Hey guys, welcome back for another chemistry lesson. In this video, we're going to talk about the Bohr model of the atom and the emission spectra associated with that. So Einstein proposed that light energy was not just and light energy. It came in these specific packets that he called quanta, which we call quanta, but you may be familiar with it as a photon. And so the energy of a photon is directly proportional to the frequency of the light that photon is associated with. It is inversely proportional to the wavelength. And then this other scientist named Planck came out with a constant to describe the proportionality of that relationship. We call it Planck's constant, which we give the letter H. And it has a value of 6.626 times 10 to the negative 34th joules times seconds. You do not have to have this number memorized. It is in your reference packet. If you somehow got to this video not through my class, then it is readily available on the internet. So this is a number you should be familiar with, but in my opinion, shouldn't have to be memorized. So these are the equations that put the frequency and the speed of light and the energy associated with those things all together into formulas. And depending on what piece of information you're given in your problem, then you can solve for any of that. So if I am given the frequency, then I would use this equation. If I'm given the wavelength, I would also need to use the value for the speed of light, but I can still find the amount of energy if I use that proportionality constant. Now the spectra that I mentioned on the title slide, that happens when atoms or molecules absorb energy and that energy is released as light. So for example, fireworks. We've seen different colors of fireworks because there are different things that are in those fireworks that emit different colors. Same thing with neon lights. We call them neon lights, but they're actually different gases that give us different colors. So when emitted light is passed through a prism, whatever color that light is, a pattern of particular wavelengths of light is seen, and that is unique to whatever atom or molecule it is that we are talking about. And this is called an emission spectrum. It is a non-continuous beam of light, and I'll talk about that again in a couple of slides. And it can be used to identify the material, and we can also do what we call flame tests. So if you have my lab, then we do flame tests in one of our labs. But the flame test will also allow you to see that. So basically, when we excite a gas by passing electrons through it, i.e. electricity, what happens is it gets really excited and the electrons go woohoo, and then they crash down. And so that light that gets emitted when they crash back down is the characteristic color of that element. So here we have this hydrogen lamp here, pass that light through a slit and then through a prism, and it splits up the light into its component colors, which we would see like this. So this is the hydrogen spectrum. Helium emits these colors. Barium emits these colors, and the white light spectrum, because it is all of the colors of light, is a continuous rainbow. So by non-continuous on the slide a couple of slides ago, what we mean is this. So it's not the whole spectrum, but it's just little tiny pieces of it. And think of these as like a barcode for whatever element it is that we're looking at. So sodium has this bright orange color because of all of the colors that compose up the light. Potassium is this pale, like lavender color. Lithium is this bright red, and barium is this like yellowish, almost white color. And so you can see from barium, we've got a lot of yellows and like yellow greens and some orange in there. So that's what gives the color here. So Niels Bohr is a really important scientist because when he was around, Ernest Rutherford came up with the nuclear model of the atom, saying, hey, we're not just evenly distributed up in here. We've got this concentrated charge in the center, right? and the electrons are just around it. Well, Bohr didn't like that because the nuclear model does not explain any structural changes that happen to the atom when energy is added or taken away, right? And so he developed his model to sort of explain what happens to the electrons when that energy is added. And this is really, really important because it kind of explains why we get those colors like we did on the previous slide. So Bohr's idea was that the energy of the atom is quantized, and the amount of energy in the atom was related to the positions of the electrons within the atom. And just remember that Einstein coined that term quanta back in like the first slide I think that we talked about. And so it's this idea that we have the specific amount of energy, right? And so the atom can only have that very specific amount of energy. So electrons, because of their fixed amount of energy, are traveling in orbits that are at a fixed distance from the nucleus. We call that a stationary state. And so what that means is the energy of that electron is proportional to the distance from the orbit, right? And so whatever happens whenever we add energy to an electron is that it will jump up. So an electron goes, let's say, from here to here. And then when it drops back down, whatever amount of energy was associated with that change in distance is emitted as light. And so the distance between the orbits determines the amount of energy of the photon of light that was produced. So here we have a hydrogen atom. And as you can see down here, we've got our little electron, right? So electron is in N equals 2 principal energy level. We add heat to it, in this case a flame test, and that electron gets excited and moves up to a higher energy level. Then, when that electron drops back down to the energy level that it came from, it emits a purple wavelength of light. And so you'll see the same thing happening for that blue-green light and that red light. And that is how we it's like the fingerprint of our elements. And so that is all I've got to say about emission spectra and the Bohr model of the atom.